Next time, I will give you some instructions asking you which question, which method you should use. Okay. Now, if you have no idea, you can compare with the examples, what I show you in the class, or the examples in the corresponding part in the textbook. Right? Usually, the reason I assign you these questions, because I have shown you some similar examples. So you should use the similar way to prove it, because I think such kind of technique is very important. This is the reason I assign you such question. You know, when I assign your homework, it's just not randomly to choose some questions. No, I based on what I taught in the class and based on what I think the technique is very important. Which technique is very important? I want you to learn this technique, so I assign you these questions. If you have no idea which method to use, you can send me an email. Okay, ask me, Dr. Chen, how can I use what method to solve this question, something like that. Okay, we can communicate, discuss. Okay, if I think okay, this method is good. For example, Alan told me now I found actually his first question proof is almost perfect. If at the very later on or at the very beginning you said based on theorem 2.3.6. to prove that this divergent, this is equivalent to prove that this converges to zero. So this is fine, but I expect you to use the definition epsilon m language. If the question is asking you to prove the convergence of sequence, you should use epsilon n language. If the question asks you to prove the divergence of a sequence to positive infinity or negative infinity, you should use n star language. Okay, something like that. Okay. Now, I want to show you the right proof. Okay. For example, 3a. We want to show a equals n squared plus 1 over n minus 2. Okay. In order to show this, prove that the given sequence n diverges to plus or minus infinity. Now first you need to give a basic judgment, right? This is positive infinity or minus, plus infinity or minus infinity. Now obviously it's plus infinity, right? And actually everybody knows that, right? Everybody saw it. Now, in order to show that this one diverges to positive infinity, you need to go over the definition. Right? Based on definition, an diverges to positive infinity plus infinity if and only if for any m greater than 0, you need to be very familiar with that definition, just like the epsilon n language, okay? There exists n star such that an greater than n for all, this means for all n greater than n star. Whenever we learned one new section, at the very beginning, if in the new section we introduce some new concept, like section 2.4, monotone sequence, okay? Now if I assign you the homework, ask you to prove that some sequence is monotone, you should base on definition. Exactly after the section that we introduce the definition, then if there's some question ask you to prove that something for that concept, you should base on definition. Okay. Now, in section 2.3, we just introduced what means a sequence is divergent to plus infinity. So, in order to show that this one diverges to positive infinity, we should use the definition. Okay. Actually, almost everyone uses the definition, but here, be careful. Similar to the some examples in section 2.2 or 2.1, when we want to prove a sequence is convergent. In that case, we enlarge some inequality. Here, we want to shrink some inequality. The reason, I will show you why. Okay. Now, for this case, we can do this way. Okay. For example, an greater than, you can write one more step. It's fine. This is, we enlarge, sorry, here should be enlarge, okay. An less than, an less than proof, okay. An less than, should we use less than or? Should be greater than, right? Greater than. Greater than n squared plus 1, for example. This is fine, right? We want to shrink, here's a shrink, right? We want to shrink. If we want to shrink this one, we have two ways. Either reduce the denominator or enlarge the top, right? So this is greater than n squared over n. So this is n. Means what? Here means for all n in n star, in capital N, we have what? An simply, right? Simply an greater than n. Right? Now, why I want to enlarge the inequality? Because based on definition, for any n greater than 0, we want to find this definition that exists n star. When we really want to prove it, we want to find such an n star. This n star should be related to this n. Just like in the definition of convergence, for any epsilon greater than 0, there exists n star. Then it means you need to find the n star relating to this epsilon. Now it's given n, you need to find this n star related to this n. Now, this is one. Now, in order to prove this one, for any n greater than 0, there exists n star such that n greater than m. Now, if we analysis n greater than m, now we already see n greater than n. So if n greater than m, if n little n greater than m, little n greater than m, then n greater than n and little n greater than put them together, right? By the transition, right? So we get n greater than n. This is what we want. Okay. Now how can a greater than or n greater than n? How can n greater than? We just pick n star to be any number, any natural number greater than n. Okay. So simply n greater than n. Okay. After obtaining this inequality, now the following is the complete proof. Okay. For any n greater than 0, pick. This definition that exists, but when you want to prove, you need to say we choose or we pick, okay, n star in n to be any natural number which is greater than n. Okay. For any m greater than 0, I pick such an n star to be any natural number in n star such that it is greater than n. Okay. Now, then whenever n greater than n star, here whenever n greater than n star just means for all n greater than n star, we have what? I want to show that this is true. That's true. We have an greater than n star such that whenever n greater than n star, right? Our an, let me see, pick n star to be any rational number greater than this one. Our an here, our an greater than n, right? An greater than n, but n greater than n star because this one. Let me highlight it. This step comes from here for all n. Then this step comes from here, right? So this is greater than n star, but n star will pick n star to be any natural number which is greater than n. So this is greater than n. We put this inequality together. This just means what? Means for any n greater than 0, we put such an n star, then an greater than m for all n greater than n star. It's just definition. Okay. So an diverges to plus infinity. Okay. In this proof, or for any such kind of example, if we want to prove that the sequence, the specific sequence, okay, diverges to plus infinity, we usually shrink the sequence. Shrink the sequence, what's our motivation? Okay. After we shrink this sequence, we get this one. This is original given sequence, okay, greater than another sequence. Now, if we can prove that this smaller one, because this is smaller than this one, right? If we can prove that the smaller one is greater than m, then the big one, of course, greater than m. Right? This is the idea. Now, let's compare with the convergence. Okay? If I ask you to prove that an equal to 1 over n plus 1, this one converges to 0. Okay? Let's see what's the difference. This time, of course, you can try to prove it, just like you did in your presentation. But now I want to use, that is a shrink, right? I want to use stretch or enlarge, okay? An here, an less than 1 over n for all n. Do you agree? Right? Less than. Now, why I want to enlarge it? Because based on definition, if we want to show an goes to 0, that's equivalent to say for n epsilon greater than 0, right? Suppose n positive, here is n positive, right? For n epsilon greater than 0, there exists n star in n such that an minus 0 less than epsilon. Now since n is positive, so this is just equivalent to say an less than epsilon, right? We are going to show that for n epsilon greater than 0, there is this n star such that an less than epsilon for all n greater than n star. This is what we are going to prove. Now, I enlarge this an to be this one. So this number is bigger. If I can show that the bigger number less than epsilon, then the small number must be less than epsilon. This is what we are going to prove. Okay? So in these two, do you get my point? Okay. To prove the convergence, we have to show such an inequality. Less than, right? For prove something less than something, we can enlarge the left-hand side. Then if we can show that the enlarged one less than the number, then original one, because the original one is smaller, of course, more less than, right? Now, to prove that a sequence is divergent to plus infinity, means we want to show that for any m greater than 0, m greater than a number. Now in this case, if we shrink an to be a smaller number, and we can show that a smaller number greater than n, then the bigger number even much bigger than n. So this is the idea. Why sometimes we enlarge it, sometimes we shrink, right? This is the idea. Okay. So this is for question 3a. For 3b or 3c, you can use a similar way to shrink it. Okay. But I know some of you, when you do the shrinkage, you sometimes this is confusing sometimes, right? Yeah. You want to shrink it, but sometimes you may enlarge it. Right? This is sometimes you may. Even me, sometimes I make such kind of mistakes. So this is normal. Then number 5. Number 5 is our homework. Number 5 is to prove that if a and b and diverge to positive infinity plus a and plus b and did I prove this one last time? No, right? Now we have two sequences, right? A and plus b and or a and times b and. most of you did almost perfect, but I still want to show. Okay. Suppose there's a question. Okay. I can repeat this question. A n and b n both diverge to plus infinity. Want to show a n plus b n plus infinity. After class, Alan reminded me to add some point to your homework grade. Okay. I should add some point to your grade. This, right? Now, based on definition, analysis, okay? Analysis. Jamie liked to give the analysis sheet, okay? For a n diverge to plus infinity, this means what? This just means for any n1 greater than 0, there exists n1 star, right? Here we can just use n, okay? We use n. Such that a n greater than n for all n greater than n star 1. This is A. That's the first one, right? Second one, based on Bn goes to positive infinity. This means for any n greater than 0, there exists n 2 star such that Bn greater than n for all n greater than n2 star. Okay. Now what we are going to show? Want to show this is what you wrote. Okay. For any, want to show is an plus bn. This one goes to positive infinity. This means for all n greater than 0, this is want to find. Okay. I don't write it exists. I always say there exists, then you in your proof you also say there exists. No, this is the definition. So-called there exists this time, you are proving it. So-called existence is what you need to find such an answer, okay? So want to find, okay? Want to find, this is our analysis, okay? Want to find n star in n such that an plus bn greater than n for all n greater than n star. Here n of course positive, right? Okay. Now why we use the same n? Right? Same n. Because here, in order to prove this one, we need to show for any given n greater than 0. When we write this sentence, it means m is given. When m is given, in the following proof, we should utilize this n. Use this one. When this sentence is written, that means m is fixed. M is existing. We can use this n to find such n star. This is what we found. Okay? Another proof. For any n greater than 0, I want to show here. But before I show here, I need to utilize these two conditions. Okay? For this n, since an diverges to positive infinity, there exists a 1 star such that an greater than n for all n greater than n 1 star. Okay, that's the first one. Second, since Bn also diverges to plus infinity, therefore there exists n 2 star. The two n1 star and n2 star may be different. Okay, such that Bn greater than n for all n greater than n2 star. In order to show that an plus bn diverges to plus infinity, we want to n star, such that this is also true, always true, right? N star. Now you need to define this n star. You need to find this n star. Okay. Now let n star to be maximum, n1 star, and n2 star. Therefore, or then, okay, whenever n greater than n star, whenever n greater than n star, but n star greater than n1 and n2 star, right? So this means n greater than n1 star. Since n greater than n1 star, we have this one. And n greater than n2 star means we have this one, right? Whenever this one, we have an plus bn greater than m plus n. Do you agree? Do you agree? When n greater than n star means n greater than n1 star. When n greater than n1 star, n greater than m, so n greater than m. Right? Similarly, bn greater than m. So n plus bn greater than m plus n. Right? Now this is what 2m. But m is positive. Right? Of course, this is greater than m. Now, what I have proved for any m greater than 0, I found an n star. This n star equal to this one, such that whenever n greater than n star, this one greater than this one. Right? An plus bn greater than n. By the definition, this just means an plus bn. W is to positive. By definition, an plus bn dials plus infinity. This is the idea, right? The idea. Now, many of you, most of you, give the proof. The proof is almost correct, right? But the description or your statements may not be strictly logic. Right? So I rewrite it. Now for an and b, an times bn, right? Times bn. Dives to positive infinity. Now in this case, you get m squared, right? Similar. And bn will greater than m times m, we have m squared. Now how can we guarantee m squared greater than m, for example? Right? Now if you couldn't see it, doesn't matter. You can do this way. Actually, we can choose m to be greater than 1. Now if m greater than 1, then m squared greater than m, right? But if you feel this, how can I guarantee that m greater than 1? Because based on definition, it didn't say m greater than 1. It only say m greater than 0, right? You can do this way. Now, if you want to show an, times bn diverges to positive infinity, we can, let me change a little bit, okay? Right? Now the proof is very similar. This is true, right? This is true, right? For any m greater than 0, let m prime equal to square root m. I can do, right? Now m prime, I just assign m prime, I just use a new variable, n prime, which is a square root of n. Now, of course, this is still greater than 0. Right? For such a m prime, since an, now you can add a little bit of more words here. For such an m prime greater than 0, then since an converges to positive infinity, then there is such a greater than m prime, right? For such an m prime, now we, based on definition of divergence to positive infinity, plus infinity, that's true. Similarly here. Then the same thing. This time this one prime. It becomes prime square. This is just there. Just there. Means an times n greater than n whenever n greater than n star. So right. Or take square root. The reason we want to take a square root because finally we want to an times bn greater than n. If we originally always use m, then an times bn will greater than m squared. This is not strictly what we want to prove, right? Now in order to let our proof strictly follow the definition, change the original and prime to be square root of that. For last question is, what's the question? You can use the ratio test. Okay, ratio test. For that question, if we want to find the n star using the definition, is very complicated. Maybe you can do it, but you still use a shrinkage or shrinkage. That is complicated. Okay. This time I didn't make the requirement very clearly, so next time I will give more detailed instruction requirements. Okay, now let's continue. Any question? It's on, but we're going to wait some time. I should turn on this Hopefully we can finish this section so that we can have some homework. We have to introduce this one, right? Last time. We introduce the definition of increasing. Decreasing can be defined similarly. Then we use several equivalent statements. Now, since they are equivalent, so in your homework, if the question asks you to prove a sequence to be increasing, you can use this one or this one or this one to prove it. Okay. Now let me just tell you the requirement earlier. Okay. This theorem says if we have an increasing sequence AN, then for increased sequence AN, we have only two possible cases. Either there is M such that if the sequence is bounded by some number, bounded above by some number, it's increasing, then it must be convergent. If it's not bounded, means the sequence will not be divergent to positive plus infinity. This is the result. For decreasing sequence, we have similar results, but it's different. For example, it still have two possibilities. The one possibility is if the sequence for decreasing, if a decreasing sequence is bounded below, for decreasing sequence, if it's bounded below, then the sequence must be convergent. Otherwise, it will be divergent to minus infinity. So for increasing sequence, if it's convergent, it must be bounded above. But for a decreasing sequence, if it's bounded below, then it must be convergent. Okay? One is bounded above, one is bounded below. And one is divergent to positive plus infinity, one is divergent to minus infinity. Now these examples. Okay. Use theorem 2.4.4 and its similar result for decreasing sequences to determine if the following sequence has a finite limit to positive infinity, limit or negative infinity. Now be careful. This question is very clear. Ask us to use theorem 2.4.4. Let's see what's the theorem. Okay, go back to see. Okay. Now this time is not to use definition, right? The question asks to use the theory. Now if I couldn't remember your homework, okay? Look at your homework now after this part when I assign.